A spacecraft has touched every planet in this solar system. A rover is crawling across Mars right now, this very second. A probe fell through the clouds of Saturn and kept whispering data back the whole way down. Crossing billions of miles of empty space has started to feel almost routine. But there is one direction no machine has ever truly gone. One place that should be the easiest to reach of all, and turns out to be the hardest. Straight up, out of the flat disk the planets share, directly above the sun, directly below it. The vertical exit from the only home you have ever known. It sounds simple. Point the rocket up and go. The problem is that physics will not let you. To understand why going up is almost impossible, you first have to understand how fast you are already moving without doing anything at all. The Earth is in motion right now. It is racing around the sun at roughly 30 kilometers every second, about 67,000 miles per hour. That is not a mistake. Every second you sit perfectly still, the ground beneath you slides 30 kilometers sideways through the dark. And every rocket ever launched inherits that motion. When a probe leaves the pad, it does not start from rest. It is already flung sideways at 30 kilometers per second, exactly like you, exactly like the planet under your feet. Normally, this is a gift. To reach Mars, that sideways speed does almost all the work. A small nudge in the right direction, a few kilometers per second of extra push, and a spacecraft is falling toward another world. But what happens when you want to go up? Not toward Mars, not toward Jupiter, not anywhere inside the disk. Straight up, perpendicular to everything. Now that free speed becomes the enemy. To climb out of the plane, a craft must first cancel the entire 30 kilometers per second it was born with. Then add new speed on top just to start rising. Mission planners have a name for this cost. They call it delta V, the change in velocity a craft has to create with its own engines. Reaching Mars takes about 4 kilometers per second of it. Climbing straight out of the plane takes close to 30, almost 10 times more. That is the prison. The orbital motion of the Earth hands you free speed in one direction and walls you in everywhere else. You can circle the sun for nothing. You can hop between planets on the same flat ring for almost nothing. But the moment you try to leave that ring, you have to fight 4.6 billion years of momentum all at once. And here is the part that breaks the mind. Reaching Pluto, 3.5 billion miles away, is cheaper than reaching a single point a few million miles directly above the North Pole of the Sun. Because that vertical exit is so brutally expensive, almost nothing has ever made the trip, which means almost everything directly above and below the sun is still, in 2026, a blank space on the map. Think about how strange that is. There are detailed maps of the surface of Mars. There are sharp photographs of Pluto taken from less than 8,000 miles away. There is close-up footage of comets, of asteroids, of the rings of Saturn and the frozen moons of Jupiter. And yet the poles of the sun, the closest star to your skin, the engine every living thing on Earth depends on, had barely been seen at all. There is a reason that should unsettle you. The polar regions are where the most violent solar activity is born. The fastest solar wind erupts from there. The magnetic field of the sun flips itself completely every 11 years, through processes that start at the poles. The entire weather of this solar system is shaped by what happens above and below the equator of that star. And for almost all of history, it has only ever been watched from the side, like trying to understand the climate of an entire planet while refusing to ever leave the equator. Only 2 missions have ever stolen a real look. The first was Ulysses, launched in 1990, a joint effort between NASA and the European Space Agency. To escape the flat plane, Ulysses could not simply climb. It flew all the way out to Jupiter first, then used the gravity of the giant as a slingshot to fling itself nearly 80 degrees out of the planetary disk. and fell back toward the sun on a steep, tilted path. The mission worked. It measured the fast solar winds streaming from the polar holes for the first time. But Ulysses was built with the instruments of the 1980s. It carried no camera that could photograph the poles. It felt the conditions up there. It never saw them. The second mission is unfolding right now. Solar Orbiter, a European probe launched in 2020, has spent years slowly tilting its orbit, stealing energy from Venus on each pass to lift itself higher above the plane. And in March of 2025, Solar Orbiter sent home the first direct images of the South Pole of the Sun ever captured by human beings. What came back was not the smooth, calm surface seen from Earth. It was a chaotic, magnetically tangled wound of a region, a knot of fields nothing like the face the Sun shows the rest of the disk. Sit with that for a moment. Until last year, no human and no machine had ever truly seen what the top or bottom of the Sun looks like. The brightest object in your sky, the most important object in your entire existence. And two of its regions were photographed for the very first time only months ago. But the poles are only half the mystery. There is a second blank space, and this one wraps around everything. Around the Sun stretches a vast bubble called the heliosphere. It is the region where the solar wind still rules, pushing outward against the cold interstellar medium beyond. Inside that bubble live the planets, the comets, and every spacecraft ever flown. Outside it, raw galactic space, flooded with cosmic rays the bubble holds back. For decades, the textbooks drew this bubble like a comet, a rounded nose where it slams into the interstellar wind, and a long tail trailing behind. It was a reasonable guess. Then in 2020, a team led by Oberth at Boston University ran a new model on NASA data and reached a stranger conclusion. The bubble may not be comet-shaped at all. The new prediction looks more like a deflated croissant, a curved bulge with two short jets curling off it and no long tail. And the reason no one can say for certain is simple and haunting. No spacecraft has ever climbed high enough above the plane to look back down and see the true shape of the thing you have spent your whole life living inside. So how do you actually break out? The obvious answer comes first. Build a bigger rocket, more fuel, more thrust, overpower the prison. And it is wrong. The energy needed to cancel the orbital motion of the Earth is so enormous that no realistic load of fuel can carry it. A rocket large enough to climb straight up by brute force would be a rocket far too heavy to ever leave the ground. The direct path is closed, which is where the answer turns inside out. The solution that mission designers keep returning to does the exact opposite of what instinct screams. To go up, you must first fall down. It is called the Solar Oberth maneuver. Instead of pointing the engines outward and fighting to climb, you aim inward. You let the spacecraft drop toward the Sun. You let it fall, faster and faster, accelerating under the raw gravity of the star, until at its closest approach, it is screaming along at hundreds of kilometers per second, possibly faster than 100 kilometers every second at the moment of perihelion. And then, only then, at the bottom of that dive, you fire the engines. Why does falling first make any sense at all? Because of something Hermann Oberth wrote down back in 1929. A rocket burn is dramatically more powerful when it happens at high speed, deep inside a gravity well. The same fuel, burned at that screaming velocity near the Sun, produces a far larger leap in energy than it ever could in calm, empty space. By burning at the closest possible point to the star, you steal the kick of a slingshot without ever touching another planet. The fuel you dragged all the way up from Earth turns into more raw motion than it could anywhere else in the solar system. And after that burn, the craft is moving so fast, in such a useful direction, that it can finally tear out of the flat plane and climb, straight toward the poles, or straight out of the system entirely. The dive becomes the launch pad. There is a second path, slower, stranger, solar sails. Mission concepts like the proposed Solar Polar Imager and the newer high-inclination solar mission lean on enormous mirrored sheets that ride the pressure of sunlight itself. No fuel, just photons, particles of light pushing on a film of metal thousands of square meters wide, thinner than the page of a book. A sail can take years to spiral its way up into a polar orbit, but it carries no propellant, and the longer it pushes, the higher it can climb. Now combine the two. A single craft that uses a sail to spiral closer and closer to the sun, then fires an Oberth burn at the bottom of the dive to fling itself vertical, then keeps riding the sail outward into the polar dark. This is the kind of mission that astrodynamicists now believe could finally deliver the first clean look at what hides directly above and below the star. Not a fantasy, a blueprint. So imagine the mission works. The dive, the burn, the long climb, all of it. What does a machine actually see from directly above the sun? First, the view goes clean. The flat plane is dirty. Earth swims through a faint haze of dust, the ground-up remains of billions of years of comets and shattered asteroids. You can see that dust with your own eyes, on a truly dark night, as a faint pyramid of light reaching up from the horizon. A craft that climbs above the plane rises out of that haze within months, into a darkness clearer and emptier than anything inside the disk. And then comes the image that has never existed. From up there, the solar system finally reveals itself as the disk it truly is. The planets frozen in their thin, flat ring, the dust hugging the plane, the vast bubble wrapped around all of it, in whatever real shape it turns out to have. For the first time, a chance to look down at your own home, the same way you look down at the Earth from orbit. And that absence is the strangest part of all. You have lived your entire life inside a structure whose shape no one has ever confirmed. You were born inside a bubble, drifting through the galaxy, and not a single photograph of it exists from the outside. Every map of it is a guess. Every drawing in every textbook is a best estimate of a thing no eye has ever witnessed. Of all the images ever pulled from the cosmos, the rings of Saturn, the dunes of Mars, the pale dot of the Earth seen from beyond Pluto, the one photograph still missing is the one looking back down at the place you actually live. The hardest direction to reach is not the farthest. It is the one straight above your head, and it has hung there untouched your entire life. So if the first mission to climb above the sun were yours to design, would you bet on the slow, patient sail drifting upward for years? Or the violent Oberth dive, falling toward the fire before it can ever escape it? Tell me below. And if you want to see what is actually waiting up there, in the dark above and below the disk, that mystery is next. This was the journey. The next one is the destination.